Welcome, ladies. Start over again. Welcome, ladies and gentlemen, to another edition of Medical Hope. My name is Bob Lovgren. I'm the host. As I always say at the beginning of the show, I talk here about the various advances that are going on in medical research, both on the basic research level, on the clinical level, and there's not much distance between them, basically. But anyway, research going on all over the world. In advances being made, it's hard to keep up, basically, and it's getting more and more all the time. As I've talked about in the past, there's many more people involved now in research of all kinds and the medical field. The big money's there, of course, for drug companies and for health for people. They want to live longer. So it's not surprising in a way, but I've talked about that before. At any rate, that's what and innovation, and it's all over the world too. It's not just in the United States. We're heavyweight when it comes to that, but China's right behind us, if not ahead of us, actually, and many other places. Lithuania, Slovenia. I talked about that in the past. Vietnam. It's recognized as a real business, basically, as far as health is concerned. At any rate, that's what I do here. What I try to do, of course, is help people as far as, I'm not a doctor, of course, but I might want to put that up there, Fred, to make sure that people understand that. I'm not a doctor, but I've done a lot of reading. I do a lot of reading and so on. And I have become knowledgeable about various things. And like I say, what I try to do here is to bring the latest advances that are really in the clinic in a way to you. But it's hard to keep up. Let's start with the book, Fred. This would be the End of the Beginning book. No, the other one. The End of the Beginning. That's deep medicine. We'll get to that in a minute too. I'll talk about that too. But let's get to you got the other one there, Fred? You don't have it?
Yeah, it's both of them.
This one?
Yeah, it's that one too.
Where is it? I can't see it. Oh yeah, I see. They're both there. Okay. All right. I'm sorry, I couldn't see it. The one as you look at the screen, the one on the right, it's called The End of the Beginning. A book about immunotherapy, where it came from, how it all started, and so on. And that's kind of the point. It's a really good history of how it all happened. It's very interesting. A lot of personalities, a lot of ins and outs, complications, conflicts, money being spent by people that don't know really what they're doing in some cases, and so on. Well, that's not true either. They all know what they're doing. They think they know what they're doing, at least. It's all over the place. And it's a historical, but it's a science book at the same time, Immunotherapy, and I highly recommend it because that is it's always a good story, basically. The one next to it, too, Deep Medicine, I didn't want to be both at the same time. I'll talk about that one, too, actually, a little bit later. That's also a very good story, Deep Medicine. In fact, a lot of it has to do with the same subject area of immunotherapy. And that's kind of what we're talking about here tonight, too, in a way. The therapy, what the body itself, what nature itself does to protect itself. The various organisms throughout the eons that life has existed on this planet. I guess I'll start out by saying that there's a battle going on, a war going on, has been for millions of years, ever since life really came to this planet. Not came to the planet, it started here in the planet, maybe it came from someplace else, that's another controversy, of course. It started. There's been a war going on the microscopic level where every day trillions of casualties, and they don't take any prisoners, millions of dead organisms, and it's constantly changing all the time. What I'm talking about here is the war between bacteria and viruses. Believe it or not, a bacteria can get a virus. A virus can attack a bacteria and kill it. Bacteria really is a very large cell, one-celled animal, one cell, whereas a virus, of course, is one cell too. But the virus is much smaller, and its whole intent in life is to get into the bacteria. That's how it in fact can survive. But they found out a lot of different things. The viruses, and that's what this is going to be kind of a disjointed story in a sense. There's viruses. Viruses, I'll just go over the list. Viruses can kill you. Viruses are bad for you, but viruses are also good for you. They can actually help you. And in fact, that's what this show is. Tonight's show is titled as Bacteriophage, which is a virus which attacks bad bacteria that is out to make you sick. But that doesn't necessarily always true. A virus can actually attack you too. There's a thing called Epstein virus, which in fact it can actually cause cancer. Epstein virus, the fact is, in some ways, I think that in fact, my picture there of my wife there in the lower left-hand corner, she's holding another dog. By the way, that's my dog in the background. There's my Facebook page. And she's holding another dog which we had when she was alive. And I think that in fact that has a lot to do with her. I was told, and it was always mentioned, Epstein-Barr virus. It's dormant in all of us, essentially. All human beings have this virus, but it's dormant in your body. It only happens when you compromise your immune system, and that's kind of what happened to my wife, as a matter of fact. But they just discovered this, that viruses can actually kill people. A virus can also help you beat cancer. It's called oncolytic virus. And the FDA has approved a few of those. And in fact, there was one called Rigvir, which I talked about one time in a show here. Rigvir comes out of Latvia, and Rig being Riga, which is the capital of Latvia, and Vir standing for virus. It was approved by Latvia, and in fact, it's actually approved by the European Union, and in places like in the Soviet Union and Tijuana, you can get this drug too, which is a virus that you use to kill cancer. So a virus can be bad, it can be good, it can do nothing for you, but and it's constantly changing too at the same time. Bacteria is the same way. They're in your microbiome, bacteria is good for you. Those bacteria, you couldn't live without them in your stomach. In fact, as they say that there are more bacteria cells in your body than there are human cells, and the rest of the cells in your body, human cells in your body. And you couldn't live without. If you killed some of those bacteria, and in fact that's what would make you sick. Your microbiome is not they have what they call the feces pill, feces treatment for people. That is bacteria essentially, which is a treatment that is used for certain diseases, for people being sick that lack a certain bacteria component in their microbiome in their body. So it can be good for you too. And again, the war is between bacteria and the virus and bacteria is a war that's been going on for many eons, almost since life began on the earth. It's been going on for forever. It in fact is a I lost my train of thought there. It is a what am I here? Like I say, this is going to be a little confusing tonight, ladies and gentlemen, because I'm trying to tie all this together. Anyway, bacteria can be very helpful to you. It can hurt you. It can have to do nothing for you. You can have it and and your immune system can go after that. And there's another element here: the immune system in your body. Very powerful, as I've said many times in the past. Your immune system is a very powerful element, the most powerful organ, really. In the system, in your most powerful system in your body. It can actually kill you if you don't control it, and that's an immunotherapy. That's always a bit of a problem. I've explained that many times before on different shows. But at any rate, I can go on and on about this. The immune system, bacteria, viruses. This constant battle going on, everyone, including you as a human being, trying to fight these pathogens, whatever weapon you can possibly use. Anyway, we're going to see a little video right now from a lady who is a professor, I believe, in Australia, and you're going to talk about this. This is something that she studies at her university. Let's see the video.
Heard about Charles Darwin and his revolutionary work on the topic of evolution, but many of us probably don't think of him as a father. In 1851, 3 of Darwin's children, including his oldest daughter, Anne, pictured here, came down with something that we would call streptococcus, but which they called scarlet fever. And tragically, his oldest child, Anne, did not survive this infection and passed away. This was 70 years before the discovery of antibiotics. And today, we could have taken her to the hospital, given her a course of penicillin, and Anne would have come around in almost every case. But this was before we had discovered these antibiotics. Today, we are being dragged back into Darwin's pre-antibiotic era. There are an increasing number of people around the world dying of antibiotic-resistant infections, and it's predicted that by 2050, 10 million people a year will die this way. The reason that this is happening is that bacteria are increasingly able to resist antibiotics. And part of the reason that this is happening as quickly as it is that bacteria have really unique ways of evolving. I'm an evolutionary biologist, and for the last 16 years, I've studied how bacteria evolve. I didn't actually always believe in evolution. I grew up in a traditional Mormon family, and we basically thought that Darwin was a pretty bad dude. Going to university completely changed my perspective, and instead of looking up for explanations, I started to look down, really far down, to the microscopic scale. And I am continually startled and amazed by the things that I find there. The microbial world is actually a little bit like a miniature and constant episode of Game of Thrones. There is a battle going on all around us at all times, and antibiotics are just one of the weapons that are being used by bacteria and other microbes against one another. I think it's important when we talk about the microbial world to remember that actually not all bacteria are bad or dangerous. And in fact, you are full of bacteria. Half of the cells in your body are actually bacterial cells, and they're called your microbiome. And we think that if we took those 10 trillion bacterial cells out of your body, that you probably wouldn't live very long. And if you did, you wouldn't be very healthy. So our bacteria are an incredibly important part of us, and we can think of them as a part of our team. But we know that not all bacteria are team players. The bacteria that make us ill are called pathogens. And they're actually the minority in the microbial world, but they get a lot of attention because pathogens can kill us. The pathogens that have acquired many of these resistance elements and are able to defend themselves against antibiotics are called superbugs. And what we are experiencing right now is that an increasing number of these superbugs are acquiring more and more resistance to antibiotics. And this is because of the way that bacteria evolve. Explaining how bacteria evolve, they do some really unique things, actually. So bacteria are able to share or swap back and forth bits of DNA. And what that means is that if a single bacterium has resistance to an antibiotic, it can swap that back and forth with other bacteria in its environment. There's really nothing like this in the animal kingdom, but you can imagine it would be almost like you're walking down the beach one day and a seagull swoops by and sneezes on you, and the next morning you could wake up with a gigantic pair of feathered wings. Awesome. We can see as scientists that this kind of exchange is taking place in the microbial world, but we're still trying to understand how frequent these exchange events are, and we're still trying to understand what the rules are. You can imagine there should be rules, because not all of these combinations are going to be great. So maybe you wake up the next morning with 2 wings, maybe you wake up with 1, or with a beak, or with really scaly feet. Not great. So we think that there are some guiding principles to how these exchange events take place, but we're still trying to understand them. So what that means is that if a single bacterium has acquired a resistance element, it can easily share that trait with other bacteria in its environment. And part of the reason that we really need to think about this is that antibiotics that we use end up in the soil and they're not recycled. So antibiotics stick around. And the consequence of that is that if we're using antibiotics and they're kind of going through our system, then we're increasing the benefit of bacteria acquiring those resistance elements. So more and more resistance takes place. The reason that we see bacteria evolve so quickly is that bacteria are the ones that invented those antibiotics in the first place. And at the same time that that happens, somebody invents the resistance elements. So they exist, they're being exchanged. The more we use antibiotics, the more we'll observe this. One of the places that we use antibiotics the most, even in a place like New Zealand, is actually in agriculture. So the majority of the antibiotics that are used right now are currently used in agriculture, and much of this use is keeping animals healthy in what are sometimes suboptimal conditions. So as we're thinking about the purchases that we make, if we're thinking about the antibiotics that we use, remember that every single use contributes in a small way to an increase in resistance. And in the future, resistance and our misuse of antibiotics now will cost real human lives. So there are problems with antibiotics, and I guess what I don't want to do is make it seem like there's no hope at all. So I want to talk a little bit about something that was used to fight bacteria and to fight infections even before we discovered antibiotics, and that's bacteriophages. Bacteriophages, or phage for short, are the tiny viruses that are able to infect bacterial cells. And these are viruses that don't have any effect on cells like ours. Bacteriophages were discovered 100 years ago, and after that time, they were used in human medicine to fight bacterial infections in places like Russia and Georgia and Poland. And these bacteriophages are actually still used in these places today to fight bacterial infections. So what does a bacteriophage actually do in nature? A bacteriophage is a protein particle that's able to kind of float adrift in the environment until it encounters its specific bacterial target. At that time, it injects its DNA into the bacterial cell, and that DNA takes over the machinery of the cell and is able to make as many as 100 copies of the phage in as little as 20 minutes. Once these are assembled, they burst out of the bacterial cell, destroying it, and go on, and each particle can then start that infection process again. So they'll amplify at the site of an infection. One of the cool things then about something like bacteriophages is that a bacteriophage is really specific. So if you put a bacteriophage in something like a human body, you can actually throw an army of them into your body, and they'll only infect and destroy the target, the bacterial pathogen that's making you ill. Which means that this is very unlike an antibiotic. So we know that broad spectrum antibiotics will sometimes go off in your body and explode like a nuclear bomb, wiping out even some of the bacteria that are really good for us and helping our health. So bacteriophages have this advantage of being quite specific. They are incredibly numerous. There are billions of bacteriophages in every gram of soil beneath our feet. Their diversity is right now not really very well known, and they each have ways of destroying bacterial pathogens that we can't even imagine yet. We just have to find them. In order to find them, one of the things that I'm doing with my undergraduate students at Massey University is becoming phage hunters. We are able to go and take undergraduate students and let them do soil sampling and find bacteriophages. And we have found over a dozen bacteriophages in the last few years. We've found bacteriophages that are able to infect Pseudomonas. So you might know some of the Pseudomonas bugs as the entity that's involved in cystic fibrosis. Another example of a Pseudomonas is the kiwi fruit pathogen PSA. This year, for the very first time, we were able to find bacteriophages that infect Mycobacterium. The Center for Disease Control has called Mycobacterium tuberculosis, or TB, the world's deadliest infectious killer. And no fewer than 1/3 of the people on the planet are infected with this organism. So we're hoping that by finding these bacteriophages, we're helping to find tools that might be useful for fighting infections at some time in the future. Finding bacteriophages is actually surprisingly simple. So this year, I had the pleasure of working with Mrs. O'Sullivan's class at Long Bay College in Auckland. These are teenagers that were able to help me find 5 brand new bacteriophages that have never been seen before. They got to name their bacteriophages. Jess named hers Morgan. Morgan named hers Jess. And there were also names like Tika, Pizza, and Dolores. These students were able to find these phages in only 3 weeks, and they did it by going to compost bins, to going to fields, going to their grandmother's gardens, and gathering up soil samples. And then we take those soil samples and we put them through a filter so that only the very smallest particles are able to pass through the filter. We then mix those and look on agar plates for places where the bacterial cells have died because of the action of those bacteriophages. These sites are called plaques. So these teenagers were able to find these bacteriophages by going out into nature, looking around, walking a lot, and they were able to find these things. They didn't even have to download an app. So, I am clearly really excited about bacteriophages. The other thing that we're able to do with them is to sequence them. We sequence these bacteriophages, and we do this with the help of the Howard Hughes Medical Institute's Science Education Alliance, which is a global cooperative team basically of university students who are finding bacteriophages that are able to destroy Mycobacterium. By doing this, by finding these phages, by sequencing them and contributing them to public databases, our team at Massey has joined really a global team that's looking for ways to destroy bacteria and hopefully to contribute to destroying infectious bacteria. Bacteriophages are exciting. Antibiotic-resistant bacteria are scary. Can bacteriophages help us today? The United States Food and Drug Administration has cleared bacteriophages for use in factories and in agriculture in order to kill infectious organisms in those settings. And bacteriophages can be put on ready-to-eat food items and prepackaged foods like cheese or like sausages. So they can be used. And around the world, there are companies that are getting interested in the idea then of using bacteriophages in their processes in order to cut down on antibiotic use and to fight bacteria. One of these is actually local kiwi fruit giant Zespri. The University of Otago has recently been involved in a project that involves Peter Finneran. They have found over 200 bacteriophages that are specifically able to kill the kiwi fruit pathogen PSA. And Zespri is looking at the possibility of using these in their processes. I would love a future where instead of using massive amounts of antibiotics, we were able to spray orchards or to spray pollen with bacteriophages that would eliminate bacterial infections before they actually get into our crops. Can bacteriophages be used in medicine for humans? I said earlier that bacteriophages are still being used today in places like Russia and Georgia and Poland on a regular basis to cure people of infections. But in the West, we're a little bit skeptical right now of using this in medicine, partly because bacteriophages are made out of protein and there might be allergic reactions. And secondarily, because it's not always easy necessarily to get a bacteriophage particle into the site of an infection. One way of getting around these types of issues is to put bacteriophages in bandages. And there is currently a clinical controlled trial going on in France testing bacteriophage-soaked bandages on burn patients. The early results of this trial look really promising, but we're still waiting to see the final results. So bacteriophages are not going to stop the bacterial evolution processes that I talked about earlier. And when we use bacteriophages, bacteria will evolve resistance. But the good news is that bacteriophages have also been evolving resistance to bacterial defenses for billions of years. On top of that, there are 10 bacteriophages on the planet for every single bacterial cell. So to my mind, the numbers are really on our side. I hope that with research into how bacteria evolve and research into alternatives to antibiotics like bacteriophages, that we still have a lot of possibility for avoiding the worst of the post-antibiotic era. Thank you.
Where do you begin? The show, of course, as its title is Bacteriophage. I think she explains it pretty well as to what it's all about. Bacteria, in this case, hang on a minute, please. I mean, I got a little bacteria going too, and that's kind of a point. Bacteria can be very good for you, as I said, in the microbiome. If you try to, if you put the virus that's out to kill bacteria, and it gets into your gut, what's to say that the virus bacteriophage would kill the wrong bacteria? It's very specific. Keep in mind, that's what she keeps repeating, and I will have to say the same thing. This bacteriophage are very specific. The virus, which is a virus now, the virus only goes after a particular kind of bacteria, only that type. The bacteria can, in fact, evolve, and so can the virus, actually. And so that particular virus, bacteriophage virus, can no longer attack that bacteria because it's changed. It won't kill that bacteria. That's what viruses do, you know. They go into a cell, into a cancer cell, into regular cells, and that's how a virus can live. There's always the question about whether viruses are really living things, because they don't really have the ability to reproduce, except if they go into another living being and use that DNA in a particular cell to multiply, as you saw in that video. That's what it does. It gets into a cell, multiplies. It sees thousands of them within 20 minutes, I think she said, something like that. And all of a sudden, the cell can't take it anymore, and it blows up, essentially. And all those things are released to go after other cells at the same time. That's what swelling is all about, inflammation, actually, when you have that situation. Well, if a bacteria, if they're good for you and they're killing the right bacteria, that's great. But what if those same viruses are killing the wrong bacteria in your gut, for example? But what if it also, as I just said before, the virus, the oncolytic viruses, in fact, can be very good. They actually kill cancer cells the same way. Only go after cancer cells that are in fact cancers. There's antigens on the surface of all these cells that identify them as being foreign, a pathogen, so to speak. And that's why the virus will attack it. Of course, that's the same thing. The immune system, I mentioned that also. The immune system does the same thing. It doesn't need a virus to do it. It initiates itself to kill the pathogens, and including bacteria and viruses. Like I say, this is a kind of a disjointed thing here, because I'm talking about here is because it's very complex. They also brought up antibiotics, and it's a big controversy about that now, giving children. You can't get your kid into a school unless he has something like 50 different vaccinations before he or she, the baby, is 2 years old, or certainly before they actually enter school at 5 years old. It's now the law in California, for example. Your kid cannot go to school. In fact, they passed even more stringent laws that you can't object to it on religious grounds, and it has to go through a doctor, and it has to go through some kind of, or if there is some kind of controversy that you want to solve, the agency now will be established in the state of California that will decide whether your child should get those vaccinations based on what you're telling them or not. It's basically their decision. No longer a decision of a doctor. It'll be a decision of a bureaucrat in Sacramento. And again, what I'm saying here tonight is it's very, like I say, it's very complex. To leave it in the hands of a bureaucrat in Sacramento, I'm not so sure is a really, really good idea. But the powers that be decided to do that. And let's face it, there's been many, many times when science and medicine has backfired, has not done what it's supposed to do. And again, why not have the natural things, bacteriophage or viruses or your own immune system? Now, I want to say up front about antibiotics, because that's a very touchy subject in people today. Let's face it, antibiotics has saved millions and millions and millions of people in life. And quite honestly, antibiotics started out, penicillin, for example, was a natural product. Some of the vaccines now that they are using for these children are synthetic. They're not natural to the body. So that's always a kind of a chance, and we don't really know what the effect is that going to be until some of these babies are in adulthood, and then they find out. I mean, let's face it. There was a drug that made funny-looking babies. It was for women who had when they were pregnant, sickness, and they take this drug. I can't remember the name of it now. I'm sure some of you know it off the top of your head. But that turned out to be not to be good. Never was approved in the United States, by the way. All the side effects were in England. The people that had malformed bodies in some cases, and so on. But again, antibiotics has been a very has saved many lives. When they had smallpox or the Black Plague, it would go through a population and kill 90% of the people. The Native American population here in North and South America was almost wiped out. Civilizations were wiped out because the Europeans who came here brought their diseases here, and there's no natural immunity. There was no natural immunity in the Native Americans for those diseases. And very, in some cases, it was actually used as a weapon. As in one case where the British gave these smallpox blankets to the Indians, and of course it had the effect that they wanted, which of course is to kill off all the Indians. But there again, it's one of those things that the smallpox is a disease that was essentially cured by injecting people with a very another smallpox vaccine called the milkmaid pox. They found out that when milkmaids didn't get smallpox, and they found out it's because they had already had a case of milkmaid milkmaid pox, and so that they were immune to the smallpox. That's another. It builds up. That's the battle that's been going on in nature, not only with human beings but with bacteria and viruses. They evolve. Some of the bacteria is able to fight back essentially, and not the viruses can't kill that bacteria because it's not the right one, not the one that they had evolved. There's been a certain out of all the bacteria and that supposedly are the same, the virus goes after that bacteria, but there's always a few in there and that are evolving to fight against that phage. That's the nature of the the battle that's been going on. But as I say, the antibiotics has been very beneficial to people. But there's some for us to now believe all the medicine that the scientists say, well, these are vaccines and they'll cure this disease and that disease and be beneficial to children, and they won't. That's why they have it for the children, because then they can go to school with other children and not inoculate them, cause them to have a disease. But anyway, that's it's all kind of, as I say, I go over the whole list again. It's the viruses, bacteria, cancer cells, the immune system. You have to add in antibiotics. That's there. It's all together. That's all part of this war that's been going on in before antibiotics, obviously. were introduced. That's a very modern phenomenon in terms of the whole flow of history here of this war that's been going on. This is a very new element, of course, the antibiotics. And I'm not necessarily being against antibiotics. I think that when nature itself has been doing the same job of killing bacteria or using good bacteria, identifying good bacteria from bad bacteria, and the virus is the same thing. They can, oncolytic virus can actually cure cancers. That's a therapy that's becoming much more studied these days. This is all part of what, I don't know, maybe nature, evolution, or God, if you will, has evolved into, has chosen this kind of method, but it takes a long time, very long time. Millions of years for this to evolve. Some people will always survive. Some animals, it's not people, some animals, some organisms will always survive the attack of the bacteria or the immune system or the viruses or all the other things that's trying to do. Some will always survive, mutate, and so they are able to fight back the pathogen. Again, it's that specificity of the various things that go after. It's only those cells they can get into, so what they call the antigens on the surface, all kinds of, you think of the cell as being some kind of closed thing, but it's not. It's an antigen is antigens and other things too on the surface of the cells. They're passageways, but you can only get through those passageways with a certain key. It's like a key in a lock, and those keys those locks are into the trillions as far as what's able to do it, what's able to get into the cell. You have to you talk about specificity. I like to tell people, you as a human being are unique, very unique. There's never been another human being on this earth like you, like me, and include all the other human beings that ever been here on the earth, on this planet, are all different. The people living today and all those that have already long since gone and into the future. There's 7 billion people here. The ability of the body to produce certain things, certain organisms, including your body, or any kind of organism, is into the trillions of different kinds of people. Of course, this is the problem, of course, with precision medicine. And that's the other book I want to show you. Want to put that book up again then, Fred? Here's another story about the same thing. This is called Deep Medicine, and it's a book by a cardiologist, actually, from Cleveland, and now he's in San Diego area. I think he works for I forgot, Salk Institute maybe, but I'm not sure exactly. Very renowned, very well-known individual. And that's what he's talking about. It gets deep. You can translate that title, Deep Medicine, really into the precision medicine part of it. They're getting deeper and deeper into understanding exactly how things work in your body. It's very complex. It's as I've said in the previous shows, it's not chaos. There is a plan to it. Again, you can call it evolution, you can call it nature, or you can call it God, but there is a plan to it. But it's chaotic, but it's not chaos. There is, in fact, a understanding of it, and that's what they're trying. That's what scientists are really trying to do, and that's the case in a sense is what we're trying to do here. Not the show, of course, but what they're trying to do with to understand all the interaction between the viruses and the bacteria and the immune system, and now add in the antibiotics at the same time, which, as I say, the very early antibiotics, and even to this day, are in fact natural products that you give to people to cause the disease in a way, but it gives them immunity to the disease. That's the immune system going on, of course, and I talked about that before. The adaptive immune system, and then the innate immune system, and then the adaptive immune system, which causes you, when you have measles, you never get measles again, because your body. I had measles. I didn't get vaccinated. I had the measles. I never had them again because in my body, I guess it's still there, is the little what they call monoclonal antibodies running around in my body looking for those measles cells, and they can't find them. They can't get them because I'm not exposed to it much anymore either. But there's of course a vaccine for measles now too, so you don't get it. Maybe we'll see. We'll see what happens. You know, the press loves to talk about all these modern things and so on, and 68 cases of measles now in New York or something like that and so on. Well, in my day, it was every kid had the measles and the mumps and chicken pox. Before I had ringworm, as a matter of fact. I guess that was, I don't know, I'm sure that's even a disease anymore. And it's good that people, you're not going to eliminate disease in the world. Like I say, the biophages are found in garbage pits and things like that. You wouldn't stick your hand into if you didn't have to. But of course, as I say, as she said in the video, she actually had some kids. I think it's New Zealand now. Had kids that go out into these places and they get to name their own. It's like naming stars. You can name a lot of stars, but you're not going to name all of them and so on. Because you found it and so on. Well, they get to name the particular virus and put a name on it and so on. How cute, I guess. But of course, there's trillions of viruses, and there's going to be a long time before they do it. I kind of played out here. Getting this idea across. I might suggest, for example, I'm going to do a show with an individual who's done shows here before, named Louis Ventura. Many of you may know Louis, and in fact, Louis is going through some real problems with a disease called Lyme disease, Lyme, by the way, named after a town in Connecticut, by the way, not the fruit. I always thought that was the case, but anyway, I guess that's me. Anyway, Lyme disease, and I'm going to do a show about it, in fact, because now there's a new drug, an existing drug right now, that in fact has been used for alcoholism. People that would take it, then they didn't want to drink, but now they found out that this particular drug is also helpful, perhaps, for people with Lyme disease. Lyme disease is a very strange disease in a way. It's hard to diagnose, for one thing. And then it has all kinds of symptoms and all kinds of things that happen to you and so on. In many ways, it's caused by a tick, and it bites you, and it passes a bacteria into your body, and it depends where it bites. If it bites in your head, you have one kind of problem. If it bites you in the leg, it's another kind of problem. And we're going to talk about that. But I'm only bringing it up because at this stage of the game, but here is a bacteria that perhaps even this bacteriophage would go after. But here again, the Lyme disease bacteria that causes Lyme disease, the bacteria that causes Lyme disease could easily evolve and not be that particular bacteriophage, that particular virus. So that could be we'll see when we talk about that. It's not quite the same subject area I wanted to talk about tonight, but only insofar as it is a bacteria, and this is the one that can harm you, can kill you, in fact. But actually, it's not as lethal as other bacteria are. That's for sure. But anyway, I thought that's why this is all tied together, ladies and gentlemen. I've been getting this. When a friend of mine mentioned this bacteriophage to me, I'll say his name is John Anderson. Some of you may know him. He mentioned it to me and thought it was something that really be investigated, and gave me something to read, and I got suggested. But then this whole area that I've been dealing with, the viruses and the antibiotics I want to do a show about, and vaccines that I want to do a show about. And of course, the immune system, which I've talked about many, many times before on this show. And of course the microbiome and all kinds of things like that. So genetic disease. And by the way, CRISPR. Here's a good example of, finish this off perhaps, to say CRISPR. I've talked about that many times before. CRISPRA. I can't remember what those letters stand for exactly now, but when I get the video, I'm gonna put it up on get my own laptop here, and I'll have all that stuff I can show you. But I've mentioned CRISPR many times before in this show and so on. How was it discovered? Well, it turns out that bacteria has a virus. Bacteria has a certain sequence on its I think they call it plasmid, and it's DNA, and that sequence is the answer when the virus attacks the bacteria, and that's what happens, of course. When it attacks it, this particular DNA matches up with the virus and is able to kill it. It's called the CRISPR, and the Cas9 is a certain 20 nucleotides, the A, C, G's, and T's letters line up, and so now the bacteria recognizes that as being foreign to it. It's bacteria's immune system, and it goes after it. So the bacteria can actually kill the virus before it gets to him, before it gets there. Now perhaps that bacteria, the bacteriophage virus, comes in, is going to kill that bacteria, and it turns out the bacteria has a weapon against the virus. So the bacteria can kill the virus, and the virus can kill the bacteria, depending on circumstances. However, they discovered this CRISPR. Jennifer Doudna at Berkeley and two other people whose, again, names I can't remember. I call him the Chinese guy from Boston, born in Iowa, by the way, and went to school in Iowa, as a matter of fact. And the French lady who is now I believe in Germany, has her own lab in Germany now. Anyway, the three of them, and others too, as again, the show I did on there, again, it goes back to the historical side of it. Like I say, this is all mixed up in things that I've talked about many times before. The historical side of it, how they found out that this is able to bacteria, and how they were able to use now for editing DNA with the CRISPR-Cas9. And there's also a lot of other things that have happened too for this same method and so on. But those three will get the Nobel Prize, as I've said before too. It gets into that, and it gets into they were able to use that method now in nature to use it to edit the gene, and certainly as a tool for identifying certain things in cells. They wanted to do when they knock out a particular cell by using the CRISPR system, or they add something to it to see what happens and so on. But it's also they're in the process. In fact, it's already in the works of the CRISPR to be therapeutic. In fact, there's 3 companies that are public, in fact, that are trying to use the CRISPR system, but it wouldn't have been found out about. It was a natural thing that bacteria do. They don't just succumb to it, but of course, it wasn't all the bacteria. It was only 1 or 2 out of maybe 100,000. It may be a few the bacteria that had that defense against that particular virus. So that virus, that bacteriophage, was able to kill all those bacteria, but it couldn't kill the other ones because they had a defense mechanism against that particular virus, and they discovered that. I say that's if nothing else, that's an unusual discovery, that a bacteria actually has a immune system, essentially a defensive system to stop a virus. And now it's being used. Again, I only have a couple of minutes here left. I guess that's another part of this whole thing, as I've talked about many times before, is most of research, a lot of research is not done by scientists in the biological field, is done not because they're looking for something and so on, they want to change nature. They're trying to find out how nature does it. In this case, how the bacteria is able to fight off a virus. How does it do that? And they've, like I say, this Eric Lander's article in the Heroes of CRISPR, they identified hundreds of people that were involved essentially in finding that out, and are continuing to do that, as a matter of fact. It could, there again, it's another therapy that could easily be very paramount in the near future. So we're talking about bacteriophages. We're talking about CRISPR systems, the immune system, the checkpoint inhibitors that are being used for immunotherapy and so on. It's all connected. It's all part of the body. What's happening, and they have to understand all those mechanisms to make it, as the book says, deep medicine. I translate that deep medicine as really precision medicine, getting deeper and deeper into exactly how things work on the molecular level, if not the atomic level, in the body. So I only have a couple of seconds left here. Let's just say that don't lose hope. There's things happening all the time to help you, and you may get lucky and get a therapy that will cure you. And it's keep watching this show, and I'll try to keep up with all the stuff that's going on. I guess as I've probably indicated here in this show tonight, it's very confusing. It's very complex, but it isn't that complex. There is a way to do it. Thank you very much, and we'll see you again.